Okay, so our situation is got a ramp, ball goes off the ramp, falls in full. So I'm going to call this delta x, and from rest, the ball would fall in 0.42 seconds. Now, if you assume, and it's a fairly good assumption for a ramp that doesn't have much steepness, okay? If you assume that the ball still falls in 42 seconds beside it, ignoring the fact that it has a bit of a vertical component to its velocity when it starts, then you're going to come to a conclusion. So I'm going to assume delta x is 28 centimeters. The ball is 142 seconds. And that implies that the velocity okay, position of the change in time is 28 centimeters over 4.42 seconds. And the reason I chose 28 centimeters, immediately is 28 is 2/3 of 42. That's going to be 3/2 of 2/3. So it'll be 66 2/3 centimeters per second. It's a very straightforward calculation. Everybody can do that. Okay. I think everybody pretty much did. I haven't looked at detail. So there's a pretty good ballpark of how fast that thing was going. If these numbers are correct, and of course, everybody estimated different numbers. So see if you followed the same procedure, but you would have divided the distance the ball went by the time fall that I gave you. Okay. Again, that's not totally accurate because, well, using this result, what were the x and y components of the end of the track velocity? Well, now, that was 3 centimeters higher at the start than it was at the end. And the track is, we're going to assume 60 centimeters. I said estimate, so you could estimate that to be, the thing that the track is actually hitting the ramp. It's at the 3 centimeter height, a little bit before it gets to the end. We're not going to worry about that. We'll just assume that it's 3 centimeters high at this end, whatever the support was, wherever the support was located. So it's 3 centimeters high, 60 centimeters. So the slope is 1/20. Now, it's this angle in here. It's the arctangent 1/20. And you can punch that into your calculator and everything, but you don't need it. Okay. What you need is V naught x is negative V naught sine theta. Got a picture here. Okay, let's just exaggerate the angle. Here's theta. And here's the initial velocity. So your initial velocity, if you would put a set of coordinate axes here. The angle would be negative theta. Maybe I ought to draw that a little bit here. I want to see it. Okay. Well, there's V naught. You got V naught Y here. V naught X here. Makes sense? This angle here is negative theta. V naught Y is V naught times the sine of negative theta. Which would be V naught times the sine of the inverse tangent of 1/20th. Right? Which would actually then be V naught times the inverse tangent of 1/20th is this angle here. Draw a right triangle with a rise of 1 and a run of 20, opposite side of 1, adjacent side of 20. Use the Pythagorean theorem, find out that the hypotenuse is square root of 399. So the sine of the arctangent is V naught times 1/20. Three and a third centimeters per second. And any piece of trigonometry course or pre-calculus course, you learn how to draw the triangle for the arctangent or arcsine or arccosine of an angle. You just put the numerator and denominator, appropriate legs of the triangle, use the Pythagorean theorem, and you have this. Now, square root of 399 doesn't vary much. And the square root of 400 is so close, it's probably out in the third decimal place, and it's probably not very big, even in that place. Okay? Figure it out yourself, you can get it. But if we use the approximation 1/20th, we get this. Now, again, something you should learn in a pre-calculus course is for small angles, sine and the tangent are practically the same. And you get that from the unit circle picture. Okay. You have a right triangle here. Okay. And the length of this leg is almost the same as the length of this arc, because the arc doesn't arc much. And the arc is actually vertical at this point, and it doesn't change much. So that proves that the arcsine and arctangent are very close together for small angles. I'm not going to go into the details of this. I'm not going to be able to teach you trigonometry, but that's something you need to look up in small angle approximations for sine and cosine. Okay. Sine and tangent. And you got one for the cosine if you're close to 90 degrees. These things are very handy. You want to get used to because you're going to probably use them. And they help you think. So, since this is a small angle, it's a little bit off. Okay. This differs from this by a factor of 1 out of 400. Okay. Which means that this square root will differ from this square root by a factor of about 1 out of 800. So you're good to within about 0.1%, one part and almost about. Now, all that is something you don't need. You can go through the whole thing and find the tangent and the arctangent, the sine, and all that stuff and calculate this, okay? I'm advocating that you understand trigonometry and the triangles and the circular model well enough to understand this because eventually you're going to need it, okay? These are important approximations. So kind of throw that away. Think about it every once in a while until it makes sense. Well, now the point of this problem though is that now if have all found from this equation, okay? You could also use this equation. You know the acceleration, either way, it's the acceleration of gravity. You know delta y, it's distance from the height of the end of the ramp. And now you know V naught y. So you get VFY. Okay. And they can average that with V naught y. You get the average velocity, divide that into the distance to get the time. This equation is pretty simple if initial velocity in this direction is 0. Okay. You could also use this equation. Okay, well, the point is, I want you to work this out. This is extra homework problem for next time. I've outlined how to do it. So, what I would ask you to do free fall from rest in the y direction, the x direction is independent. This implies V naught which implies V naught y, which is not actually equal to zero, no, we use that as our first assumption. V naught and theta gives you V naught y. That's actually that a triangle. You know, any two things in this little triangular diagram, you know they through. Okay. And you should kind of work that out, make sure you understand that. And that looks like something. It's not equal to zero. V naught y isn't zero. You use these three quantities to get V naught y. And that comes back and gives you a better estimate of delta t. Which you could then cycle into this whole thing. Now using that delta t, you can get this and this, and you're going to get an even better estimate of delta t. And you could iterate that process. You set it up in Excel and let Excel iterate it for you. Just means repeat the loop for each t. Okay. And you can find the actual delta t and figure out the actual velocity. Okay. It's fairly involved. Now, ultimately, we're going to want to be able to analyze, be able to figure out what V naught is. Okay. Just based on how far the ball lands in the straight drop position and the height of the tape. It's a hard problem. Talk about it. I don't think I'll ever require you to do it, but if you can, it'd be great. Well, that's a situation that I can use kind of an introduction to projectile motion. Projectile motion is pretty simple. You got the x direction and the y direction, and the only thing they have in common is the time. Okay? Time keeps running no matter what happens in x, no matter what happens in y. So in the x direction, well, for example, you have you can write your v t equals a times t plus v naught, but you put an x subscript on v naught and on v, because that's what you would observe. For example, imagine you're 100 feet high looking down on this thing at night, and you got little LEDs or some light that illuminates the ball as it rolls. All you're going to see is motion in this direction. Okay. Once the ball's off the edge of the ramp, air resistance is pretty much negligible. So whatever velocity, it speeds up, speeds up, speeds up, gets there, and then it just maintains that velocity till it hits the floor and breaks and the light goes out or whatever. Okay, that makes sense? Imagine seeing this from above where you can't see motion in the up and down direction. That's what it's going to look like. And if your x acceleration is 0, then this isn't there, right? Now gravity has no component in the x direction. It's purely in the y direction. Okay, it's negative 10 meters per second squared j plus 0 I. You use the I and j vectors. Okay, so you have this. And for an ideal projectile, this is our assumption. So this is assumed. Then you have I've written ideal case a little small, that's all that says. It's not always true. You got significant air resistance, then, well, then you better know some differential equations. And we're not doing that in this course. Okay. That's about all you need to know about the explosion, isn't it? You got an equation for the velocity, you got an equation for the position, you don't need it anymore. Okay. Now, for the y direction, y is a function of time. V naught y is not generally 0, as is the case in what we just looked at. You've got a non-zero y component, which causes the thing to get to the floor a little faster. Okay. And what if there's no y? And g is the acceleration of gravity. Say that y of t is y naught plus v naught yt plus 1/2 gt squared. And we're going to put a y naught in there because typically for a projectile, you're at some height above what would be your zero height. Okay, like if you're firing a cannon from a hill and it's going to land on a plane below, then you probably want that plane to be y equals 0, although you can set y equals 0 any place you want. Okay, if you want to choose y equals 0 at the position of your cannon, then your ground is it's lower is it a negative position, right? Y is negative. All right, so that's pretty much what we need, but then we could write it like this. This is your average velocity, that's your time. This is average of your initial final velocity, that's your time. We're assuming uniform acceleration g. So that might be handy. And then we write this fourth equation motion of this one. Okay. So there are your tools. And these are independent. Well, suppose no problem. Kind of along the lines of what we've been talking about with track. So got a ball rolling along here. It lands at distance h below. At distance delta x relative to its initial position. Its initial position being when it left the ground. Okay. So what can we say about this? If we know v, it gives v naught and h, what's delta x? Okay, for example, you know it's 120 centimeters per second times the I vector plus 0 times the j vector. In other words, motion is horizontal, 120 meters per second, 0 in the y direction. And minus 20 meters. And what's the horizontal range? Question is, how can we use the y direction to determine the x motion? Start with what we know. What do we know about these symbols in the y direction? Okay, so first thing we might want to look at is this equation here, or identify some of our variables. What is 0 here? That's the initial y velocity, which makes this a whole lot simpler, doesn't it? What's v naught? what's the I component? That's V naught X. This is delta Y, or Y of 0, which means Y naught. Implicitly, we're starting our time at 0, t equals 0 at the instant this thing leaves the ramp, okay? All right, well, what can we do with that? We don't know the time of fall. We don't know Vy. Well, actually, we do know Vy at any time, but we're not given the final Y velocity. So we're not going to be able to yet determine much of anything in this relationship. But from this one, we know G, we know V naught Y, which is 0, which makes things simpler. We know Y naught, which is H, right? And we know that the Y we're looking for is 0. Okay. So we can use this with Y naught equal H, Y of t equals 0, find time of fall. Okay. Well, we don't have to use this thing formally. We can simply reason it out. Using slightly different symbols. Delta Y is 0. Acceleration equals negative G. And delta Y is 0. Delta Y equals, we're writing out correctly, sorry. Okay. Otherwise, this A equals negative G, AY equals negative G. You get 10 meters per second, negative 10 meters per second squared. And delta Y is this. To delta Y over G, which in this case, I believe is 2 seconds, because delta Y is 20 meters, negative 20 meters. That I'll be able to take it. Okay. You're going from 20 meters down to 0. Delta Y is negative, well, I'll write it out. Equals the square root of 2 times your negative 20 meters divided by negative 10 meters per second squared. That's the square root of 4 seconds squared, which is 2 seconds. In other words, given your height and that your initial y velocity is 0, it's very straightforward. Figure out what the time of fall is. That makes sense? Should. You've done hopefully problems on free fall. Did you have free fall in the chapter? Chapter 3? Yeah, it was there. I think maybe 2 problems, maybe 3. Yeah. I'm pretty sure. Okay. So, I mean, you should be familiar with this. Yeah. This should be something that just kind of logs in, no matter what symbols I choose to use. Knowing your initial height and your final height is 0, right? I should have put into the picture y to 0 to ground so that the initial y position is h. In this case, negative 20 meters. Now, having that, can you figure out your delta x, range of this projectile? Figure it out quickly, if possible. At least sketch it out. Okay, I don't know how much of that I can record. But again, over here, I think we use y naught equals h, v naught y equals 0, and figure out y at any time. The y that we want is 0. Y naught is 20 meters. I didn't say y naught equals 0. I might have. But anyway, y naught is 20 meters. Y naught equals h. That's 20 meters in this case. So you can formally take this equation with the value of g, which is negative 10 meters per second squared. If you want to do a quick calculation, negative 9.8, whatever it is here that we don't know. Okay. It's probably close to 9.81. If you want to get really accurate about it, you would use that. But just to solve the problem, I use 10 meters per second squared and then do 20% correction. Anyhow, we get t equals 2 seconds. Now, if you just reason it out with the scheme I talked about in class on Wednesday, you got your 5 variables for the y direction. Okay, you know delta y, you know a y, you know b naught y, you get delta t. Right there it is. Okay, and you got to use an equation of motion. Okay, so I use essentially this equation. You get delta t equals 2 seconds. Now you do the x motion. What do you know? You already knew the initial velocity in the x direction. You knew the acceleration in the x direction. I didn't write it, but it's 0. Okay. You get delta x, 2.4 meters.